as I mentioned in the lecture 4 thread, this is kind of experiment to go through the notebook in this lecture recap instead of the pre-recorded lecture. And the reason for that is this notebook is mostly supplementary for the most part. Mostly for the most part, whatever. So there's also a lot of code in here that you aren't familiar with or will get familiar with starting next week and the week after. So you don't have to know everything in this notebook. So it's mostly just for your reference if it helps you understand stuff. So the slides and the lecture videos are more than enough for the SQL lecture. And I think it's more important to get practice yourself in the lab and the discussion. All right, so hold on, open chat. So is this notebook available? Yeah, so if you go to the lecture 4 thread or the lecture 4, the page on the website, there's one of the links on the top is an HTML copy of the notebook. So it's basically this notebook but in a HTML format. And there's also a link to the code which syncs the notebook to your data hub, and then you can play around with it there. All right, so this first cell, these first 2 cells are just importing stuff and then connecting to a SQLite 3 database. And then we create the 2 tables we saw in the joins part of the lecture. So this is S with primary key ID, T with primary key ID. This has breed, S has name, T has breed, and then we insert the values. So that's all this cell's doing. And then this is just a nice way to print out SQL queries. So here, this thing basically prints out the SQL query and then the output of the SQL query. So that's all you have to know for this. You have to understand what this is doing. So I can do select star from S where, hold on, there's a lot of, okay, it's all searches. I could do select star from S where ID is greater than or equal to 2. It prints out the query and it prints out the cats that have an ID greater than or equal to 2. And then cross joins. So we saw that selects every pair of rows from one table and the other. So here there are 4 rows in, as you saw in lecture, there are 4 rows for these for ST. So there would be 16 rows in the output of a cross join. So for apricot, you would join it with all 4 rows. So you would have basically 4 rows for every row in the left table. So for apricot, I would join it with all 4 values from the right table. For boots, I would join it with all 4 values in the right table. For Callie, I would join it all 4 values in the right table, and then for Eugene as well. So that's a cross join, and then an inner join is just combining the values that have common IDs. So you saw in the lecture that there were 3 different syntaxes that you can do. So you could do this. You could do select star from S inner join T. That's the same thing. Or you can do select star from S comma T where S.id equals T.id. And all 3 of those are equivalent. So you can choose whatever you're most comfortable with. And then yeah, so only the rows with matching IDs appear in the result. And then if we do a left outer join, we get all the rows from the left table. So in this case, the left table here is S. So we get all 4 rows from the left table. And if there's a matching record in the right table, then we fill in the values there. Otherwise, then we fill in null values. Hold on. Open the chat so I can actually see. Is there any difference performance-wise for the joins? I think I'm not 100% sure of the answer off the top of my head, but my best guess is that under the hood, there are query optimizers that usually do better on inner joins and inner joins basically. And normally when you're doing a inner join, you don't act the underlying SQL database management system doesn't actually do this cross join first and then like filter out all the rows afterwards. It does like some special processing so that like it can do this query much faster than having to output the whole cross join and then filtering it down. But my best guess is that left and right outer joins and full outer joins take longer than inner join, because inner joins are very common compared to inner left outer joins or like outer joins in general. So usually because inner joins are so common, query optimizers under the hood are more optimized for inner joins. Great question. But it's not really something that you have to worry about in this class. If you want to know like more about it, feel free to like look at CS 186. Where was I? Inner join, left join. So you can't do a right join in SQLite, but you can in like other database systems like Postgres. So for the sake of just like showing alpha right join, you can basically, all you have to do is like switch the tables of S and T and you get a left join. And if you really want like the same output as the lecture, you can just select the columns like the opposite way as well. So this would take all, so this is basically just this, but I do the left join on T left join S, which means I'll keep all the rows in the T table instead of the S table. And then similarly, the records that don't match are none. And then I could do, you can't do a full outer join in SQLite either, but you can do this like kind of hacky way of doing it where you union the result from S left join T and T left join S, and you'll get like all the rows for a full outer join, which is all the rows in both tables, even if there doesn't have matching, even if there aren't matching records. What does union do? Yeah, so union, you don't have to know about this, but union, basically it selects all the rows here and then union all of these rows. And if they're duplicates, then union only takes one of them. So here you'll see like if these two queries, like these three rows appear in both of these two queries. But when I do union, it gets rid of the duplicate, so it only keeps one of them. So it only keeps these three. It basically takes all the rows of the two tables, combines them, and gets rid of duplicates. Any other questions on joins before I jump into some of the other syntax? Yeah, this is weird. I'm just like talking to a screen.
I'm here, don't worry.
Yeah, all right. Yeah, so these few cells just like download the notebook or download some IMDb data from the IMDb database, which is just a database of like movies and like animated films and stuff like that. So this will take a while. If you're doing it, I have these cached, so it takes a little bit shorter time, but if you're running this like by yourself, this will usually take much longer because you have to actually download the data and like unzip it. So here, this is just saying like pd.readcsv, you'll see that like next week. Basically that just reads all the data from this CSV file, or in this case it's a TSV file, which is tab separated values instead of comma separated. So all the difference, the only difference between comma separated and tab separated is that like you separate the values with commas instead of tabs. So the reason like this doesn't work well is because if I see how many like rows names has, you'll see that there's like 10 million rows for the names data set. So if I try to read all that into a pandas data frame, depending on like how much memory you have, that might like completely crash your computer or your kernel basically, because you don't have enough memory to store all of these 10 million rows inside of memory, which is why we have to use things like SQL because that can fit in, like you can use SQL for larger data sets that don't fit in memory but like fit on disk. So if you're doing this, if you're walking through this on your own, you'll have to run these four commands in the terminal instead of like in the notebook. So an example of that is if I go here and I open up a new terminal, and then I can, so I have my notebook in like some weird like SU20 real directory that I called. But if I go into the lecture directory and run SQLite 3, let's see, what's the command again? SQLite 3 imdb.db. SQLite 3 imdb.db. So that'll open like a SQLite 3 thing, and then I can like run these three commands. And then after this will take a while if you're doing this locally, but after you run these commands, you'll be set for like the rest of the notebook. And if you don't run them, then like the rest of the notebook will error. So yeah, this will take a while. And then what we can do is look at like the word count. This is just like exploring the data a little bit more. We can look at the word count. This is going to take a while because it has to go through all of the words in the TSV file. So this first thing is like the number of lines in the file. So here there's 10 million, like I mentioned earlier, for names, and then for titles, it's around like 7 million. Don't worry about like the rest of the output. This is like the number of words, and like this is the number of bytes. Head just looks at like the first 5 rows of the TSV file. So this helps us get a idea of like what these two tables actually look like. So we got titles, which is basically just a bunch of movies and like what type they are, when they were made, and like how long they run for. Names are names of like actors in these movies. So like Fred Astaire, and like when they were born, when they died, and like what professions they have. And known for titles is just a list of movies that they are known for. The first movie is like the first one listed here is the title that they're most well known for. Yeah, so these refer to like this tconst thing here. So tconst and nconst here are just primary keys for the titles and names tables respectively. This is just some random identifier that they choose to identify the titles, and this is just some random identifier that they chose to identify the names. So you can run those. So here we're just making a SQLite, like moving this into SQLite, and I'm just getting the 10 tables. I mean the first 10 rows in the titles table. And then we saw in lab 2 that we can look at the schemas of these tables using this like select SQL from SQLite master thing. And this will tell us like the schemas of these tables, like titles has a tconst text, and the names has like an nconst text. Interestingly, it doesn't like show tconst as like a primary key and nconst as a primary key, but those are the actual primary keys for that table. This is just some syntax. You can do in Python, what you can do is like format, these are like called format strings. So you can like name your variable to some string and then like output it using like this syntax here. So again, we can get like 10 movies from the titles table. And we'll see that the runtime minutes here is like, it's a string when you output it. So we saw in lecture that you can cast these to ints, and that makes it so that like you can process them as integers instead of strings. So here, this is a query that looks kind of complex, but it's not really that complex. So this is the same as before. You're selecting the title, you're casting the runtime minutes, which was originally a string, to an int. You're casting the start year, which was also a string, to an int. And this is just like renaming it to title, name, and year. So what this is doing is we're looking for movies that are action movies. So if there's like an action as a part of the genre somewhere. So remember that if I do like percent something percent, that means I'm just looking at whether that something is in the title or in the genre of the movie at all. So anything that actually has the word action as a part of the genre, that would appear in our result. And anything that doesn't have the word action in it as the genre, it wouldn't appear in the result. So this is just some filtering. I'm looking at movies that are in the 20th century or later, and I don't want adult films, and I want to make sure that it's a movie, not like a short or something like that. And we're just looking arbitrarily for movies that are between 60 and 180 minutes long. Oh, there's a question. We use and percent for strings only. Yeah, so only kind of makes sense for like strings, because you're looking for whether that string matches a particular string here. Is it case sensitive? I believe so. So if I try percent action with the lowercase, maybe it's not. Let me try a random query and see. So where primary title like Carmencita. So that works. And if I lowercase Carmencita, still works. So I guess it is not case sensitive. Does not use the same way as like? Yeah. So if I do not it won't. Let's see. Yeah. So like would output like Carmencita here, but if I do not it'll just output everything that's not like Carmencita. Yeah. Does that answer all of your questions, or are there other questions here? So there's a question, if we edited the SQL lecture file on Jupyter Notebook, how do we reset it to original? So what you would have to do is go into your data hub and delete this, shut it down first and then delete it. And then go back to the lecture link and re-pull it. Or you can go to, what Serge said, you can go to the DS100 data 100 repo for summer 2020 and look at the files there and download it from there. Okay. Let's see, where was I? Yeah, so these are all the action movies filtered by some extra criteria. And we want to check how big is this table? Is it 2 million rows, or is it more like 10,000? And we'll see here this is 21,000 rows, which is safe enough that we can read it, or small enough that we can read it into a Python, a CSV file, or not a CSV file, but a Python pandas data frame, which you'll see about later, which you'll see what that is next week, but you'll see what that means next week. But you can think of it similar to a table from the data science module in data 8. So here I'm just reading this into a pandas data frame. This is just the shape of a data frame. Here are some plots that you might not exactly know how to interpret right now, but you'll be able to interpret in 2 weeks from now when we go over visualizations. But this is just a histogram of the years, so you'll see that there are more action movies in recent years. This is a scatter plot of the time in the year, so this is kind of a mess. And we'll talk about why this is bad plot in the visualization lectures. This is just like a smooth estimate of this plot, so it's a bit like easier to read. And then this is a line plot of like the year over time, the mean, sorry, the mean, hold on, the mean running time per year. Yeah, so it's already 1 p.m. So feel free to go if you want to. But I'm just gonna finish this walkthrough real quick. Hopefully, I don't have too much left. And then this is a box plot of the year per decade, of how much the time, like how long each movie is per decade. And again, you can see like the later years, the movies are getting longer. The action movies are getting longer. Again, I wouldn't worry about understanding these plots right now. Maybe like after you learn about visualizations, you can go back at these in like 2 weeks and understand what they are. I'm gonna answer all the questions after like going through the notebook, so like just for time. So we saw sampling. You can select everything for a movie and then order by random limit 3. And the limit here is just like how many like what the size of your sample you want. So order by random just like orders it in a random order, and then you just take like 3 random rows. So this takes a SRS of size 3 from the action movie table. And we also saw in lecture that we could take 3 random years by just doing select year from action movie group by year. That will select all the like distinct years. And then if I order by random limit 3, then I'm taking 3 random years. You'll see like every time I run this, like I get 3 different random years. And then you can also select all the movies from 3 random years. This is called a cluster sample, but again, you don't have to know exactly what that means. And then like, let's look at the query first before looking at this. So select star from action movie where year in this thing. So this thing was the same, same query as here, where I just selected 3 random years. So I'm just looking for all the action movies where the year is in these 3 random years. So this will select all the action movies in those 3 that came from like those 3 random years. Let's see. All right. I'm just going to rush through the rest because we're already over time. So this is an example of case. Usually case appears in the select. So here we're just selecting if the time column or the time attribute is less than 70, then we output short. Otherwise, if it's less than 120, then we output medium. Otherwise, we output long. So this just outputs. This selects like the ID titled time year column, and then a separate column called length that like is short if it's less than 70 minutes, is medium if it's less than 120 minutes, and otherwise it's long. And then that's without a base expression. If I want to use a base expression, what I can do is case year like %197%. And then if that's true, then that's a 70s movie. Otherwise, it's not a 70s movie. So then I get not 70s if the year is like not in the 1970s. Okay, subster. So what we can do with subster is basically, we saw that there's like this really long list of known for titles. We can only look at the first one by using like the subster syntax. So the actual syntax of subster is a little bit complicated and different from like what you're used to in Python, but you don't have to, for the purpose of this class, you don't have to understand like what exactly these arguments mean. So last thing is that let's look at like some age trends for the movies in this data set. So this query is just selecting the name and like the the year, the birth year, and then the movie ID. So again, the first what's it called? The first entry in the known for titles is the movie that the name that this particular actor or actress is most known for. So they're actually not just actors and actresses, they're like producers and directors. So that was not correct. Yeah, so here now we can select whether it's an actor or actress by using like again in the case when. So if the primary profession has actor in it somewhere, so some of these have like a bunch of random professions like combined. This is just seeing whether actor is in there somewhere. And this is just seeing whether actress is in there somewhere. And if I do that, then I can basically tell whether they're an actor, an actress, or an actress. And if I do this, I'll get a table of the actors and like whether they're actors or actresses, and like the movie ID that they're most known for. And I can join this with the action movie table I made earlier, and that'll give me the title of the movie, the action movie that they're most known for. And we can do random things like see which actors are known for like vampire movies. And finally, this is just some extra processing that, again, you don't have to really understand until like 2 weeks from now, that plots the age of the actors and actresses in the action movies they're known for. So you'll see like actors are generally older, or the actors are generally older for the action movies that they're known for. All right, so that's it for this. Any questions before we wrap this up? All right, yeah. Again, I want to reiterate that you don't have to understand pretty much most of this notebook, because a lot of the syntax is, you won't go over the syntax until like 2 weeks from now when you learn about pandas and visualization. So I wouldn't worry about like understanding every nook and cranny of this notebook. It's mostly supplementary and for your own reference if you want to look at it later.